Hello everyone. In this lecture, I want to talk about the basis of centrifugal pump selection and design. And more precisely, we will learn how to select a proper pump and motor at a specified flow rate for a defined system. Here are the titles that we will cover during our article. But before we go to the design part, we will go through some theoretical knowledge that practical parts make more sense. Flow movers are the heart of the process, and pump, which is one of those, is used for moving liquids by adding energy to the fluid in one or more of the following ways: by increasing pressure, velocity, or elevation. The net result is to facilitate the movement of fluids from one point to the other point with higher pressure. As an example, in pipeline system, elements of pipeline system are including pumps, control valves, meters, tanks, and other equipments. There are many types of pumps, and we select the best one for our application. The most popular type of pumps in industry is the centrifugal pump. As we can see from the pump performance curve, the shape of head versus flow diagram should be anything like this, depending on the pump parameters. Such curves are known as pump performance curves, which can be determined experimentally by manufacturers by using a flow meter and pressure gauges. As we can see from curve, NPSHR is increases with flow. Regarding to efficiency curve, since power gained by the flow is different from the power received from the pump, we have this diagram and curve due to different type of losses. There is an operating point in pump that the efficiency is maximum, and it is known as best efficiency point. As we can see, pump head almost always decreases with increasing flow rate. In this curve, the last point is the theoretically maximum head possible. This is true, but only in ideal cases. In practice, there are a lot of energy losses associated with pump flow, which this maximum head cannot be reached. As we can see from the diagram, power almost always increases with flow. Here is the deadhead or shut-off pressure, which is where the head curve crosses head axis at zero flow rate. As we can see, we select the design point almost always near a best efficiency point. There's a good point here that the power curve at zero flow rate is not zero because this power is not going to fluid. At zero flow, it is this energy is going to system. Pumps are equipment that add hydraulic energy to liquid. This energy consists of three elements: pressure head, velocity head, and elevation head. As we can see from the Bernoulli equation, it consists of each of these terms. Head is the elevation the pump can push a fluid in a pipeline at a specific flow rate. As we can see in these two vessels, head at the outlet of vessels are the same, while pressures are different. Because head is independent of density, while pressure is head multiplied by density. There are some rules of thumb for pump selection. First, select a good flow point, which is best efficiency point. Near this point, pump can have longer life and lower maintenance possibility. For earlier design, put some room for future expansion in case larger impeller is required. The last but not the least is net positive suction head. In order for the pump to move fluid, the system must be able to push fluid into the pump as fast as the pump can push it out. Therefore, there must be a certain minimum required suction pressure for each pump based on the flow. NPSHA, which is available by the system designer, is higher than NPSH required, which is required by system and is given by manufacturer. In order to prevent cavitation, we should consider how to select an NPSH. Net positive suction head required when liquid is pulled into a pump. The flow into the suction causes a slight drop in pressure. Before pressure is increasing through pumping, this pressure drop is related to the pump design and flow rate is called NPSHR. When the liquid is close to its boiling point, a drop in pressure can cause boiling, which in compression lead to cavitation. So one should always ensure that NPSHA, which is pressure inlet absolute minus pressure vapor pressure, is higher than NPSHR. Flow in the system can change based on the valve opening. So we can define system head based on specific flow rate as a specific valve opening. This blue line shows the system curve, which is the sum of the friction plus static head. As an example, in our system, we need a pump that will output 2480 foot of head at roughly 26,000 gallon per minute. If both the pump curve with the ideal impeller and speed and system curve are plotted on the same graph, the steady-state flow rate will be where the pump curve, which is head supplied, and the system curve, which is head consumed, intersect. In this case, we are getting 13,200 gallon per minute when we require 25,850. How we can get the higher flow rate? Absolutely, by adding more pumps. So we would put multiple pumps in series to get the higher head that we require. This graph shows two pumps in parallel. They have the ability to flow up to 60,000 gallon per meter. However, the head has not increased, with almost the same intersection point with system curve as when we had only one pump. And lastly, 4 pumps in series. As we increase the number of pumps, the flow rate is increasing only a little bit, and when we add more pump, the less it increases. This graph shows 4 pumps in series. They have ability to increase head and at almost the same flow rate. The control valve is used to vary the resistance to flow by throttling, which is effectively modifying the system curve. In a fixed speed pumping system, the PCB is used to absorb the excess head to achieve necessary flow or pressure. PCB convert this excess energy to heat, vibration, and to noise. Remember that the intersection of the system curve and pump curve is where the steady-state flow will occur. So, if we wish to move the steady-state flow rate, the delta P across the PCB will be pump head minus the system head at the flow rate we wish to achieve. This would give us this modified system curve shown here and new intersection which shows here. This new system curve is shown by dashed line. Power is the rate of transferring energy. Power is related to flow rate, pressure loss, and density. Almost always, more flow rate results in more power. We need to be able to estimate the cost of pump and pick a good one, or to do cost estimation, since we need some idea how much a process will cost to build or to operate. Pumps, like other mechanical devices, are not 100% efficient. Generally, they are about 77% efficient. Based on our calculation, we see that the power is equal to flow rate multiplied by head multiplied by specific gravity divided by efficiency and 5310, which is a constant for unit conversion. If we assume that the power, each kilowatt per hour of power is 0.1 cent, we can find the cost of power for this pump. In practice, there are a variety of energy losses associated with the pump flow, such as pipeline and control valve losses, which are the major friction losses in the system. This loss increases quadratically with velocity. I mean the loss for flow friction. Another loss is when there is a sudden contraction or expansion, which is also proportional to the velocity square. This was the last slide for this part. Thank you so much for watching this lecture. Next lecture would be on solving some examples related to pump sizing. If there is anything that can help me to make it better, please don't hesitate to leave me comments. Your feedback is greatly appreciated. Thank you.